Hello everyone, I'm Loic Rouquette. I'm a PhD student at Int'l. Today I will speak about the work done with my PhD advisor, Solnon. We are working on a project dedicated to cryptanalysis on symmetric ciphers, and our goal is to improve the scalability of CP solvers. On this paper, the main attacks are the differential attack and the relay key attack. They were introduced respectively in 1991 by Biam and Shamir and in 1994 by Biam. The aim is to compute the maximum differential characteristic. The basic idea is to analyze what is the impact of a modification of an input on the output. Here we have a cipher function f that transforms a plaintext A in a ciphertext A with a ka. The plaintext, the k, and the ciphertext are binary sequences. Now we choose another k and another plaintext. The cipher function transforms the new plaintext with the new k into a new ciphertext. We compute the differences between the inputs with the bitwise XOR operator. The bitwise XOR operator is defined with the following truth table. The result is 1 if the two inputs are different. On the same way, we compute the differences between the two k's and the differences between the two ciphertexts. Since cipher algorithms contain nonlinear subfunctions called S-boxes, the probability to observe the output difference given the input difference is non-uniform. Our goal is to find the differences in the input and the differences in the output that maximize the probability to appear. Computing the maximum differential characteristic is expensive. To counter this drawback, Knudsen introduces in 1995 the notion of truncated differential. The idea is to cut the bits in sequence of size k. Usually k equals 8, and we cut the bits in bytes. Each byte is abstracted by a boolean that indicates if the differential byte contains at least one non-null bit. The maximum differential characteristic is now computed in two steps. In the first step, we enumerate all the abstract solutions that activate the less S-boxes as possible. In the second step, for each abstract solution, we compute all the concrete solutions, what are the full binary sequences, and we look for the sequence that has the maximum probability. To be able to work on this abstraction, it's necessary to define the abstraction of some operators. As the bitwise XOR operator is widely used in cipher processes, we are working to improve it. The abstraction of the XOR operator is noted with an empty circle. The result of the XOR between two null sequences is an empty sequence. So 0 AbstractXOR 0 is equal to 0. The result of the XOR between a non-null sequence and a null sequence is null. So 1 AbstractXOR 0 is equal to 1. The result is the same if we inverse the non-null and the null sequences. The last case is when we have two non-null sequences. If the two sequences are equal, then the difference becomes null and 1 AbstractXOR 1 is equal to 0. But if the two sequences are different, then the difference remains non-null and 1 AbstractXOR 1 is equal to 1. The last case introduces information loss, and enumerating false positive abstract solution is costly. To counter that, we need a more powerful filtering. This can be done in different ways. David Gero generates new equations to improve his filtering, and our solution was to create a dedicated global constraint. The contributions of the paper are the introduction of a new global constraint called AbstractXOR, which is modeling and speed-up solution process. We prove that the satisfiability of AbstractXOR is an NP-complete problem. We present a relaxation of AbstractXOR for which the satisfiability problem is polynomial. We define two propagation algorithms, one that checks feasibility and the other that ensures R consistency. Finally, we present some results for two attacks on Midori and AES ciphers. The presentation is done in three parts. In the first part, I will present the abstraction of the bitwise XOR operator and the AbstractXOR constraint. After that, I will present our result on Midori and AES ciphers, and finally, I will make a conclusion. The binary string is cut in sequences of size k. Each sequence delta I is abstracted by a boolean big delta I that indicates if the sequence is empty or not. More formally, big delta I equals 0 means that the sequence delta I equals 0, and big delta I equals 1 means that the sequence delta I can take any value which can be represented in k bits except the value 0. In CP, the abstraction of delta A XOR delta B XOR delta C equals 0 is represented by a sum over the Boolean variables. The problem is that this solution is not sharp enough. Now we will see how AbstractXOR can improve the filtering. On this example, we have 5 bytes that are abstracted with a Boolean and a system of 2 equations. We want to know if the abstraction of the sequence B may take the value 0. On the abstraction, we have 2 sums over the Boolean variables. The first sum is equal to 3, so the inequality is satisfied. For the second equation, the sum is equal to 2, so the inequality is also satisfied. To conclude, the abstraction says that big delta B equals 0 is valid. On the other side, we have the concrete system. The first equation does not contain B, so it is not useful. But in the second equation, we have delta B is equal to delta D XOR delta E, and this is non-null. So the concrete system says that big delta B cannot be equal to 0 even if the abstraction accepts it. To define AbstractXOR, we have C, a set of concrete XOR equations, K, an integer that defines the size of the sequences, and X, a set of Boolean variables. We define AbstractXOR say K of X is satisfied if and only if there is a realization of X on the domain 0 to power k minus 1, which satisfies C. On the previous example, C is a set that contains the 2 equations. K is equal to 8 since we are working on byte, and X is a set of Boolean variables. Now, if we look at the results, as we know that delta B is a non-null byte, we have big delta B equals 1 is a valid solution, and big delta B equals 0 is not a valid solution. If we keep this definition of AbstractXOR, the satisfiability problem is an NP-complete problem by a reduction from a graph coloring problem with 2 power k minus 1 colors. I will not explain the details here, but the intuition is that a XOR equation may be viewed as all different constraints. A XOR equation system can be represented by a graph where each node is a variable and an edge from A to B indicates that A and B belongs to the same equation. To make the satisfiability a polynomial problem, we remove the upper bound constraints. Now AbstractXOR say of X is satisfied if and only if there is a realization of X that satisfies C. AbstractXOR works with a special representation of the XOR equations. We represent the XOR equations by a matrix that is in row-reduced echelon form. On the bottom, we have an example of these representations. The RRE form has its property. The first non-null variables are called pivot variables and only occurs in one equation. The other variables are non-pivot variables. And we also remove the variables that are assigned to 0. The satisfiability problem is done in 3 steps. We remove the variables assigned to 0, we maintain the matrix in RRE form, we filter the domains according to the selected consistency, and finally AbstractXOR is satisfiable if and only if every row of the matrix contains at least 2 non-null cells. The satisfiability problem can be checked in polynomial time. Now I will speak about the filtering rules. As the theorem says that the matrix must contain at least 2 non-null cells, if an equation only contains 1 variable, we remove the value 1 from the domain of this variable and we remove the variable from the system. Now we will see two other cases to ensure global arc consistency. The second case occurs when one equation contains two variables. If one of the above variables is assigned to 1, then the second variable must also be assigned to 1. Last case is a little bit more complex. If we have two equations that contain the same set of non-pivot variables, and the pivot of one of the above equations is assigned to 1, the pivot of the second equation must all be equals to 1. The proof is that if we have two variables that are the result of the same set of variables, they are equal. We go back to our first example. We will only use the satisfiability rule, that is, a variable that is alone in one equation must be assigned to 0. We create the matrix from the equations. We remove big delta C from the system since it's assigned to 0. Now, if we try to assign big delta B to 0, we must also remove the variable from the system. Now, the system is no more in row-reduced echelon form since the second equation doesn't have a pivot. We transform the system to be in row-reduced echelon form. And now we apply the first rule on big delta A since it's not the only variable of the first equations. As the domain of big delta A only contains ones and one must be removed, we detect an inconsistency. So big delta B is not valid. Now we want to assign big delta B to 1. We restore the matrix to the previous states. As the matrix is already in row-reduced echelon form, we do not change it. All the line contains at least two non-null cells, so AbstractXOR is satisfied if big delta B is equal to 1. Now I will speak about our experiments on Midori and AES. Firstly, I will present how AbstractXOR is used to model cipher processes. On the left, you can see the representation of Midori cipher. On the top, we have the plaintext and the key, and on the bottom, we have the ciphertext. The other states are the internal state computed during the process. Note that the operations are done airtime, which is the number of rounds of the cipher process. Since the plaintext and the ciphertext can be freely chosen, we ignore them. The first operator is the S-boxes. As a reminder, we want to maximize the probability to observe the output difference, knowing the input difference. As S-boxes are nonlinear, they degrade the probability. In the concrete step, we want to maximize the probability for the S-boxes, and in the abstract domain, we fix the number of active S-boxes and keep it as small as possible. In the concrete step, the S-boxes are represented by a type constraint that gives the probability to observe the output difference given the input difference. In the abstraction step, the only abstraction we have is that a non-null input difference will give a non-null output difference. The second operator, called shuffle cell, performs a permutation between the bytes of the state. The abstraction representation is nearly the same as the concrete one. The third operator is mixed colon. The result, the state Z, is equal to a multiplication of a fixed matrix with the state Y. The multiplication is done in Galois field 2 power 8. I will not give the details here, but since the fixed matrix only contains zeros and ones as coefficients, the operation can be represented by a set of XOR equations. The last operator is called k-add. It performs a XOR between the k and the state at the end of the round. As mixed colon, the abstraction of the k-add operator is done with AbstractXOR. As you can see, the abstract model is fully extracted from the concrete problem and doesn't require extra knowledge. As previously said, we want to find the differential characteristic with the maximum probability, and this for a given number of times. The problem is done in two steps. We enumerate all the abstract solutions, And for each abstract solution, we search for the maximum differential characteristic. We have three models for both Midori and AES. Two models that use AbstractXOR, they are called Global Fees and Global GAC. Global Fees only check feasibility, and Global GAC ensure arc consistency. The last model is called Advanced. To improve the filtering, Advanced generates a new set of XOR equations from the initial set of XOR equations. Global models are written in Choco for both steps. Advanced is executed on pcat set, which uses the Ling solver for the step 1 and is written in Choco for the step 2. Midori was designed as the lightweight version of AES, so the both ciphers look alike. The main difference are the case schedule function, which is not present in Midori, and the mixed colon operation. In Midori, the matrix used in the mixed colon only contains zeros and ones, and can be represented directly with XOR equations. In AES, the matrix contains coefficients greater than 1 and requires a different abstraction. The first chart represents the time done to find the maximal differential characteristic for Midori in both 64 and 128 bits. The reality key allows to inject the differences in the K. The x-axis is the number of rounds and the y-axis is the computation time. The first line of the chart represents the time done to enumerate all the abstract solutions, and the second line represents the time to solve the full problem. That is the step 1 and the step 2. As you can see, global models offer good performances against the advanced model, and Global GAC is a little bit quicker than Global Fees on Midori 128. Now we will see the result of AES. The presentation is the same as previously. On the first line we have the time for the first step, and on the second line we have the time for the full problem. Here the results are more mitigated, since the CP performances are really impacted by the heuristic. Nevertheless, global models offer good performances on AES 128. On AES 256, all the instances can be done before the timeout. The worst cases appear on AES 192, where two instances cannot be solved in 3 days. Now we have the result for the single key attack. The single key attack allows to only inject differences in the plain text and not in the case. Global models are the only that can resolve 5 rounds of Midori 64 and 4 rounds of Midori 108 in less than 1 hour. Moreover, as the two steps are mixed in the same model or global models, they can solve the full problem of single key attack for AES with 4 rounds. To conclude, AbstractXOR simplifies modeling and perform a better filtering. It also speeds up solution process on Midori and some instances of AES. As we think that advanced models benefit from the close learning of SAT solvers, a possible improvement is to add close learning to the constraints, and another work is to use AbstractXOR to solve new differential attacks. Thank you for watching.